Hi, good morning everybody. Welcome back to the class of rate processes, and we were in reaction dynamics, molecular reaction dynamics. So, in our last lecture we started our discussion with molecular reaction dynamics, and it started with elementary collision process between structureless reactants like hard spheres. So, basically molecular dynamics is the dynamics of molecular collision. Okay. So, dynamics of molecular collision is the study of molecular level mechanism of elementary chemical and physical rate processes. Okay. Process may be elementary chemical or may be elementary physical. Physical means no chemical reaction is taking place. Okay. It seeks to understand what actually takes place when a net change, that is maybe a physical or maybe a chemical, is occurring. Okay. Suppose two gases are like A2 plus B2, I mean diatomic gas, one A2 another B2 is introduced in a container, and maybe what is seen is that no reaction is taking place. We are expecting maybe 2 AB, but reaction is not taking place. Okay. Collision occurs between A2 and B2, but no exchange of atom is there. So, so we would like to study such elementary reactions, possibility of such elementary reactions, and we want to probe and we want to promote maybe. Okay. So, this is what we are going to elaborate, this particular point. Now, in our last lecture we have been discussing this conservation principles. Conservation principles. Conservation principles. Okay. That is energy conservation, and angular momentum. Angular momentum conservation. Maybe rotational angular momentum and maybe orbital angular momentum, or a combination of that. That is in between your reactant to product. Okay. There has to be conservation of energy. Suppose this reaction leads to a change in enthalpy of this much. So, maybe plus minus whatever. So, left hand side total energy and right hand side total energy, that should be conserved. In the same way, left hand side total angular momentum and right hand side total angular momentum must be conserved. Now, next is the forces and potential energy factors. Okay. Now, forces like molecular forces are operative, like that is we would like to understand the forces which control the interaction, forces that control the interaction, interaction between reactants. In one dimension, for a diatomic system like A B, a diatomic system, the potential energy curve looks like something like this with separation, okay, where F r force is minus del V or del r. Okay. So, so it is in one dimension, but suppose two reactant molecules are interacting like this, okay, then it no longer remains confined in one dimension, rather a three-dimensional description of this potential is needed, which is called the potential energy surface. In that case, I mean a multidimensional description is required. Like in that case, only this coordinate is not sufficient, maybe another coordinate has to be introduced in order to account for the approach of another reactant from all possible directions. Okay. Now, next we will move on to experimental options. Experimental options, that is, we have to select the energy and quantum states of reactants. So, selection of energies and quantum states. For reactants. Okay. So, that is, and also in the same way we have to probe the energies and population, okay, and quantum state populations in the product as well. That is the product which is created, which is formed because of reactants. So, reactants and also products. Okay. And we have to ensure that when there is a distribution in different quantum states for the reactants and also for the products, then that should not be scrambled due to collisional exchange of energy. So, that has to be ensured. So, that is why we have to adapt a specific a very specific technique. Okay. One technique could be molecular beam experiments. Okay, what is that? That you have got a container in which your reactants are there. So, gaseous reactants, and there is a small orifice, maybe its pressure is of the order of several torr, maybe of the order of 10 torr. Okay. And this side there is high vacuum. Okay. So, the source, I mean from the source, this reactants will effuse like this. Okay. So, this source will act as effusive source. Okay. And the distribution of various speeds will be F c will be something like this. Okay. It's like this distribution of speed. Okay. And energy, average energy will be in the lower side. Okay. Now, another situation could be created. Okay. Another situation could be created like that you have another source where where the pressure is very high. Pressure is very high means of the order of 10 to the power say 3 torr. Okay. And of course, this side is high vacuum. Okay. So, the molecules will come from higher pressure to lower pressure side, high vacuum. Okay. And this will act as, this source will act as a supersonic nozzle source. Nozzle source. And your distribution F c versus C will be more shifted in this region, and it will be narrower. Okay, it will be narrower, but you see this one and that one, it is more shifted to this direction. Okay. So, it is a supersonic source where you are getting a narrower distribution, but here it is a wider distribution. Okay. And your this is more wide compared to this one. This is less. Okay. So, velocities can be selected with, here in this case you use a mechanical chopper. Okay. Mechanical chopper can be used to select different velocities. I mean, like you can select maybe this portion, maybe this portion with the help of a mechanical chopper. But what will happen for this? Now, in this case you have to use a different carrier gas. Okay. Different carrier gas to select velocities. I mean, velocities can be tuned with the help of various carrier gas. Maybe carrier gas means maybe nitrogen, maybe like argon means the gas which are not reactive. You can select with the help of carrier gases, you can select various velocities. Okay. Next, what we can measure from this, from such an arrangement, I mean molecular beam experiment, what we can measure, what is the net aim using such molecular beam arrangement, that in one case you use an effusive source, in another case you use supersonic nozzle source. Okay. So, here you have to use carrier gas to select for selecting different velocities. Okay. So, so what are you going to measure? What can be measured? So, what to measure? What to measure? What to measure? Now, we want to measure cross section experimentally, reaction cross section. So, cross section experimentally, reaction cross section experimentally. Okay. Now, reaction cross section may be regarded as an effective target area for the reaction to occur. Okay. It is the effective target area. Target area means, suppose you have got a dartboard and you want to throw the magnet on it. Okay. So, your dartboard is the effective area, and suppose those situations where magnet gets stuck onto the dartboard corresponds to an effective collision and reaction. So, that means within that particular area, if you can throw, if you can keep your target, and if you can hit that, then the reaction will take place. You can think in that way. Okay. So, it is the effective target area for the reaction. to occur. Okay. Now, in simple collision theory, we started with collision theory that it is an elementary process, that is if you go back to our earlier one of our earlier lectures, that if you think of reaction mechanism, okay, you will be finding that sometimes it is complicated and it is composed of a number of elementary reactions. It is not that a simple A and B combining, A plus B C giving rise to A B plus C. It is not simple reaction. Something happens. Suppose the mechanism is such that, say, B C dissociates to form B and C, and then A plus B producing A B. It may happen, it may so happen, or maybe in some other way. So that so basically it is composed of a number of elementary reactions. Okay, and each elementary reaction can be considered to be like means if it is a gas phase reaction is occurring maybe via collisional mode. Okay, so using elementary chemical elementary collision mechanism, where collision is the means by which reaction is taking place. If it is an atom exchange reaction, say if the collision is effective, then atom is exchanged from one entity to another entity, giving rise to a product. So that is why we started with simple collision theory, and the number of collision is very much important. I mean, it is an important factor, but not all collisions are effective. Only certain fraction of the total collisions, okay, of the total collision is a certain fraction of total collision is effective in bringing a chemical change. Okay. So, so in simple collision theory, this cross section is defined as pi cross section. So, simple collision theory cross section is defined as is basically pi d square, where d is the sum of the radii of two spheres, like this is one sphere and this is another sphere. Okay. So, maybe sum of the radii. So, this is your cross section. So, this plus that, this is your d. Okay. So, basically suppose we have got, say, BC like this. This is your BC and its cross section is like this, and say A is approaching this way. So, maybe it will approach, it may do like this, something like this. Okay. So, it moves this way, it is approaching from this side. So, A is going this way. Okay. So, what is this? So, if you think in this way, that you have got two concentric circles, concentric circle. Okay. So, this is say B and this will be say dB, say this is dB. So, this area between the two concentric circles, this area will be 2 pi b dB. Now, what is this B? Say this is B. Now, if we think of simple collision theory, thinking in terms of collision theory, that B can be regarded as, so you see that this is the closest approach, I mean the closest that a reactant can approach this BC. Okay, it cannot, you know, it can be maybe more than that, but that is the closest approach, because that will give some effective collision. So, the distance of closest approach of two particles in absence of any external force. If there is any other force, then it may be different, but in absence of any external force, this could be the closest approach. So, B may be regarded as the distance of closest approach, and it is a measure of closeness of collision. If B is small, collision is more, B is bigger, then collision probability will be less. Okay. Now, in classical physics, now the cross section is defined in this fashion, that sigma is the cross section which is nothing but equal to, you know, a function which, you know, represents the reaction probability. So, P B, that is probability with B value, P B into 2 pi B d B. So, 2 pi B d B is this, then it is a probability factor which is called the probability reaction probability, or it is called the opacity function, and you have to integrate from 0 to say B max. So, maximum value of B that one can reach. Okay. So, what is this this PB? PB is the opacity function, and it represents the fraction of the collisions with impact parameter B that gives rise to chemical reaction. Okay. Now, what is this opacity function or reaction probability function? Let us try to understand what is this opacity function. So, opacity function. So, remember the expression, cross section sigma is equal to integral 0 to B max P B into 2 pi B d B. So, 2 pi B d B is coming from this area. So, 2 pi B d B is this. Okay. Now, this reaction cross section governs the rate of those collisions that lead to a chemical reaction. Okay. Now, it is a measure of the effective size of the molecule as determined by their ability to reaction. Okay. And it is necessarily smaller than the total collision cross section, which governs the rate of all collision. And as the reactant collide at a given energy, so when there is a collision, then we characterize the initial approach in terms of the impact parameter, and we define in terms of this opacity function. Okay, opacity function P B. Okay, and it is the fraction of the collisions with impact parameter B that leads to chemical reaction. And this opacity function has two properties. Okay. One is, at most all collisions lead to reaction. So, P B could be unity. So, all collisions lead to chemical reaction. Okay. So, that means this value, I mean, it will be 0 less than equal to P B less than equal to 1. I mean, when this is 0, that means other possibility is all will lead to chemical reaction and none of them lead to reaction. So, that is why this range. So, Pb will range from 0 to 1, in between 0 to 1. So, that if it is 100%, then Pb will tend to be 1. If it is nothing, then Pb will be very close to 0. And for a chemical reaction to occur, it is necessary that atoms or reactants, to approach closely, so that chemical forces will operate and necessary atomic rearrangement may be possible. And for high impact parameter, collisions, when impact parameter is high, high, the collisions occurring at the centrifugal barrier. So, collisions to centrifugal barrier, and this will act to keep molecules apart. So, since it is centrifugal barrier, means it is a repulsive barrier. So, this will tend to make them apart. So, when impact parameter B is high, collisions to centrifugal barrier and leading to less reaction. Therefore, we expect that reaction will only take place when B is small, that is when impact parameter is less, that is of the order of range of impact parameter, order of range of intermolecular forces, then reaction will take place. So, if Pb is 0, then reaction does not take place, and that corresponds to high value of V. That corresponds to high value of B. So, in terms of opacity function Pb, what can we write? So, the thing is that if the impact parameter is high, impact parameter B is high, that is it is a measure of closeness. It is a measure of closeness. So, impact parameter high means collisions to the centrifugal barrier, and if impact parameter less, then intermolecular force are operative and a reaction may take place. That is when V is small, that is of the order of range of intermolecular forces, then the reaction is expected to occur. Now, in terms of opacity function, again we can write the reaction cross section sigma, or rather d sigma r, which is equal to twice pi b Pb dB. Then if you integrate, then you will be getting sigma. Upon integration, you will be getting sigma is equal to integration from 0 to some B max 2 pi Pb B dB. This way you can express sigma. Now, here 2 pi b Pb dB is the element of total collision cross section, and Pb is the fraction of effective collision. Now, what happens is that total cross section, total reaction, cross section for the reaction, maybe it is divided into effective and non-effective, that is reactive cross section and non-reactive cross section. You can subdivide into two. So in that way, for non-reactive cross section you can write d sigma non-reactive, which is equal to twice pi b into 1 minus p b into d b. So, p b is the effective, and as I told you that p b will range from p b will range like this. Okay, it is a measure of effective, I mean probability of reaction to occur. So, that means this represents the probability of reaction that is not, I mean means probability that reaction will not occur, I mean the collisions which are ineffective. So, non-reactive cross section may be written in this fashion, non-reactive cross section. So, this is the total cross section, I mean reactive cross section, and this is the non-reactive cross section. Okay. So, that is this factor. Okay. This factor is the fraction of collisions that are non-reactive with the impact parameter b. Okay. So, impact parameter may have some value, but maybe this means with a given impact parameter, this is the fraction of the collisions that are not reactive. So, fraction of non-reactive non-reactive collisions. Okay. When of course with b, impact parameter b. Okay. So, we have to remember one point, that while we are distributing, we are partitioning the impact parameter. Okay. I mean partitioning the cross section into reactive and non-reactive one, that is reactive collision. So, collisions reactive and non-reactive, reactive and non-reactive. So, while partitioning between means in between this, okay, we note that while we are partitioning between these two, that sum of the cross section will have always, means we have to partition in such a way that the sum of the cross section will have to be like total will be like this one, sum of the total. We have to partition in such a way that it will be 2 pi b dB irrespective of whatever it is. Okay. That means if the reaction has several different paths, then what is needed, that now suppose paths with means if the reaction has several paths, okay, which are energetically possible. Of course, if energy does not permit, then it will not happen. So, energetically possible, then if out of many paths, suppose one path is promoted, I mean one cross section of one path is, if it is increased, then that has to affect the other, I mean that should increase at the expense of the reduction of the other path. So, that is very important. Okay. So, that means their cross section, I mean the cross section of other path which is energetically possible, the increase of cross section can happen at the expense of the decrease of another, that is, or at the expense of non-reactive cross section, that is maybe non-reactive cross section will be reduced and that will be transferred to that will be converted to a reactive cross section. Okay. But it will never be more than 2 pi b dB when the impact parameter is b. So, that is the limit. So, that is 2 pi b dB is the limit. Okay. And final outcome of collision with B in the range B to B plus dB. I mean, you have to think of that B is ranging from B to B plus dB, so that your this value becomes 2 pi B dB. Okay. So, so reaction cross section, I mean, you can think in this fashion. Okay. Next, let us look into a simple opacity function. So, opacity function. Okay. Now, a determination of reaction cross section cannot uniquely specify Pb. Okay. So, if you determine reaction cross section sigma, it cannot uniquely determine Pb. Okay. But it determines its B weighted value. I mean, basically it is an integration between 0 to B max. Okay. So, it is cross section 2 pi B dB into Pb. Okay. Since P is dependent on B, so you will be getting, when you determine this, you will be getting the B weighted magnitude. Okay. Let us, rather than trying to find out this Pb, let us assume some simple functional form with very few parameters. Okay. Parameters to understand it. Okay. Now, let us think in this way, that we have a step function of kind, I mean, let us have its functional form like a step function such that Pb, let us think in this way, Pb is equal to 1 when B is less than or equal to B max, and is equal to 0 when B, impact parameter B, is greater than B max. So, this will be just like a step function, that it remains flat for certain situation, and then it becomes 0. Okay. So, this is the cutoff value, say this is your cutoff value. Okay. Means somehow if B is a little more than B max, it will give you 0. So, it has to be within B max, then it will be 1. So, it is a step function. Okay. That is the highest B, I mean B max is the highest B with which the reaction can only occur, and beyond that it will be 0. So, in that case what will happen, that your sigma will be equal to twice pi integration from 0 to B max your B dB, and in that case it will be giving you pi into B square max. Okay. So, pi into B square max. Okay. So, this way you can think of. Okay. So, you have got your Pb 1 for certain value, that means your, say its representation is, I mean graphical presentation is Pb. Okay. It is say 1, it remains this much, and this is your say B max. So, this is 1. So, beyond B max, the value it is just like a step function, it is a square pulse kind of thing. So, it is 1. Okay. So, that in that way you will be, means assuming some specific functional form, means rather than rigorously trying to determine the determine Pb, consider some simple case, and then we should be able to able to find out, we should be able to find out the sigma. Okay, so this is about impact parameter and the opacity function, that is the reaction probability function. Okay, so where are we at? That PB, now PB is the opacity function, is the reaction probability function, which is also termed as the opacity function, and it represents the fraction of collisions with impact parameter B that will lead to chemical reaction. So, therefore, cross section. So, cross section can be thought of as something that is averaged like as I told you that the dartboard description. So, it is thought of as dartboard average of reaction probability. Okay. So, the sometime opacity function is difficult to determine. So that is why using some simple functional form, simple as I use this step function, you should be able to find out the cross section, because opacity function could be a complex description. Okay. So, next we will move on to types of encounter. Okay. So, it is an encounter process, as I told you, that simple collision theory, we started with simple collision theory, that collision occurs between reactants, and as I told you, reactants are structural as maybe atomic collision, and importantly that is your impact parameter B. As I told you, that first we have to think that impact parameter for the description of impact parameter, as if there is no attractive or repulsive force operative, and then we think that means we introduce that there is some attractive or repulsive force which is operative between reactants, and then that operative force, that is repulsive or attractive, will be determining the effective collision, whether the collision will be effective or not. So, that is why when as I told you that impact parameter, if it is low value or if it is high value, then the situation will be like PB, that is the opacity function, will be in one case it will be very low, in another case it will be high, that is probability, reaction probability will be less, maybe reaction probability will be high. That is when your collision occurs at the centrifugal barrier, then possibility of reaction is less. So, high impact less reaction, but low impact possibility of reaction will be more, that I already have told you. So, next is type of encounter, that is here the most important thing is encounter. Okay, encounter is important. So, it can have categories, it can be categorized. Okay. One is elastic scattering. So, first is a encounter. So, one is elastic scattering, okay. Another is inelastic scattering, and third is reactive scattering. Okay. Third is reactive scattering. So, what is this elastic scattering? that conserves the kinetic energy and lead to change in the direction. So, conservation of kinetic energy, but that will lead to maybe change in the direction, change in the direction. Okay. It is elastic, inelastic means that will lead to change in the internal energy of colliding entities. Okay. So, that means basically what is happening, that there means entities are colliding. So, if it is elastic, that means perfectly this momentum is transferred here, this momentum is transferred over here, and this momentum is transferred over here. So, exchange of momentum. So, this one was initially moving in this direction and that one was initially moving in this direction. The moment they are colliding, their direction has been reversed. So, that is why there is a change in direction for your elastic scattering. Inelastic scattering, collision, maybe because of certain degrees of softness that may happen, because say your atoms may have some finite volume. So, when they collide, then maybe there is some kind of initially they are bigger, the moment they are colliding there is a squeezing or something, some kind of effect happening. So, that exactly the translation to translation is not occurring, translation degrees of freedom to translation degrees of freedom, maybe other modes are activated, okay, and as a result of which internal energy is increasing, not the translational, but the internal energy of one is changing. Maybe this one is also has suffered from change in internal energy. Okay. So, therefore, that leads to change in internal energy of the colliding entity, which is called inelastic scattering. And the third category is the reactive scattering, that leads to the rearrangement of bonds. So, reactive scattering leads to rearrangement of bonds within reacting species. Okay. So, that means say you have got A plus B C giving rise to A B plus C. So, as if this bond has migrated in between this and C is freed. Okay. So, that is this this scattering has led to effective chemical reaction. Okay. So, this reaction, I mean this scattering has led to effective chemical reaction. Okay. So, these are the types of encounter that we have to consider. Okay. So, what we have told so far. Now, the important point is, while considering chemical reaction, I mean in chemical dynamics, I mean reaction dynamics, we should focus on the reactive collision, because reactive collisions are important for chemical reaction to take place. Okay. These are very important for the chemical reaction to take place. Now, Now, again I would like to mention one point that that the book that that we should means you may consult is the book by Raphael de Levine. That is also a book on chemical, molecular reaction dynamics, and another newly published book that is by Tutorials in molecular reaction dynamics, okay, by Broward. It is edited by and Valence. Okay, these two are the books, or maybe other books are also there. Now, today we have we focused on forces, potential energy and forces. Then we have talked a little about one dimensional case, and then maybe later on we will come to potential energy surface, that is a multidimensional energy landscape. Now, we also talked about experimental requirement for selecting velocities. One is this effusive source we may have to use. Maybe in other case it is supersonic nozzle. So with supersonic nozzle we can select different velocities using various carrier gases. And then we talked about reaction cross section, which may be regarded as the effective target for the concerned reaction. And we also have introduced the opacity function, that's a probability function, that's a reaction probability function. And also we have introduced this B factor, that is the impact parameter factor. And as a typical case, we have considered a step function for this PB, that is opacity function, and tried to find out this sigma, that is reaction cross section. And we also talked little about types of encounter that are responsible for that may be important, and especially reactive scattering, which we will take up maybe later on. So I guess that's all for today. Now, next we will in the next lecture we will take up experimental measurement of cross section, and maybe we'll talk about crossed beam experiment. Okay, so till then have nice time. Thank you.